Welcome to our video lecture on VSEPR theory. Our objectives for today: we're going to define VSEPR theory. We're going to distinguish between lone pairs of electrons, sometimes also called non-bonding pairs of electrons, and bonding groups of electrons. We're then going to use that information to predict molecular and electron domain shapes based on this super cool thing called VSEPR theory. So VSEPR stands for valence shell electron pair repulsion. This makes a lot of sense. So valence shell, we're talking about those valence energy levels. Electron pair, we know that in covalently bonded molecules, we have pairs of electrons being shared. Because all those electrons are negatively charged, they repel each other. Basically, electrons want to be as far away from each other as possible. And we can use that information to predict the shapes of molecules based on the bonding and non-bonding electrons around the central atom. It's a lot of words. Let's talk about what even is a central atom. It's the atom in the center. That's pretty easy. So for carbon dioxide, whoa, I missed. For carbon dioxide, it's going to be that carbon. And this molecule here in the middle, it's going to be that nitrogen. And of course, over here in water, it's going to be oxygen. So we're just looking at the central atom, the atom in the center of the molecule. That's super important when we're trying to predict the shapes. So now we're going to think about this difference between bonding and non-bonding electrons. Looking back here at carbon dioxide, these electrons are in a bonding group. These electrons are also in bonds. I would call that another bonding group. I've got a double bond and a double bond. Technically, I only have two groups of bonding electrons. I only have two bonds. They're both double bonds, but I only have two bonds. So 1, 2 bonding groups around that carbon. There are 0 lone pairs or non-bonding electrons. So there are no electrons on carbon that are not in bonds. That's not true for nitrogen here in NH3. So remember that these lines represent bonds. There's a pair of shared electrons in every bond. So nitrogen has 1, 2, 3 groups of electrons in bonds. Nitrogen also has this one non-bonding pair. Sometimes we call those lone pairs of electrons. So one lone pair and 1, 2, 3 bonding groups on that central atom, the nitrogen. Water, again, those lines are representing pairs of shared electrons. I've got 1, 2 bonding groups on that oxygen, 1, 2 lone pairs, non-bonding groups of electrons around the central atom. So let's look at how we can use that information to predict the shapes of molecules. So first up, we're going to look at lone pairs. We're going to look at bonding groups. If, and I'm looking at this molecule right here, top left, there are 0 lone pairs. There are no electrons on this molecule that are not in bonds. There are 1, 2 bonding groups. And so this shape is going to be linear. It's going to be linear, and it's going to have a bond angle of 180 degrees. Easy peasy. Makes a lot of sense. If I have 0 lone pairs of electrons, but 3 bonding groups, 1, 2, 3 bonding groups on that central atom, we're always looking at that central atom, 1, 2, 3 groups of bonds on the central atom, then we're going to call this trigonal planar. Planar is related to the word plano in Spanish, which means flat. It is a triangle shape and it's flat, trigonal planar. Bond angles of 120 degrees, 120 degrees from here to here, 120 degrees from here to here, 120 degrees from here to here. Now we're going to get a little bit quirkier because we're going from 0 lone pairs to now we have 1 lone pair. So this molecule here, top right corner, we cannot see the lone pair of electrons. It's not included in our picture, but there is a pair of electrons here that are not in bonds. So we've got 1 bonding group, 2 bonding groups, and then 1 lone pair of electrons on that central atom. These guys take up space just like these guys take up space. We're going to call it, its electron domain geometry is still going to be trigonal planar because I still have 1, 2, 3, 1, 2, 3 things on that central atom. But only 2 of them are actually in bonds, and so my molecular geometry is going to be called bent because it looks like it's bent. The bond angles are going to be less than 120 degrees. this angle right here is going to be slightly less than 120 degrees, maybe about 118 degrees. The reason is this: those non-bonding pairs of electrons actually take up a little bit more space than do the electrons in the bonds. And so these two guys get squeezed together a little bit closer to each other, not by a lot, just by a little bit. We go from about 120 degrees to 118 degrees. We're going to add more things to that central atom now. If I have 4 bonding groups on my central atom, I'm looking at this guy right here. 1, 2, 3, 4. 4 things on that central atom. The angles between all of those atoms are going to be 109.5 degrees. It's not 90. It might look like 90, but we are thinking in 3 dimensions, not 2 dimensions. And so we can kind of push things back into the screen, up and away from the screen. So all of these bond angles are 109.5, 109.5. We're going to call it tetrahedral. Tetra means 4, and we've got 1, 2, 3, 4 things on that central atom. Tetrahedral is the name of both the electron domain geometry and the molecular geometry. This guy here, we cannot see it, but there is actually a pair of non-bonding electrons on the central atom right here. And so these guys are taking up space, and then there's 1, 2, 3 groups of bonding electrons. 1 lone pair, 3 bonding groups. 1 lone pair, 1, 2, 3 bonding groups. Because there's a total of 1, 2, 3, 4 things total on that central atom, we're going to call this electron domain tetrahedral. But if I'm thinking about just the molecule's shape, I'm looking at just where the atoms are, then my shape is instead going to be called trigonal pyramidal. Trigonal pyramidal, trigonal pyramidal. Because I've got 1, 2, 3 things on that central atom. Let me see if I can erase some of my scribbles here. I'm going to erase some of those scribbles. So going back, here's my central atom. There's 1, 2, 3 things on that central atom that are in bonds. So my molecular geometry is going to be called trigonal because I still kind of have a triangle. But because of that lone pair of electrons that made the electron domain shape tetrahedral, that 1 lone pair of electrons that are here, these electrons are actually going to push these guys down a little bit. And so the bond angle is going to be not quite 109.5, but just a little bit less, maybe like 107, maybe like 107 degrees, a little bit less than 109.5 because these guys take up some space and push the legs of that pyramid a little bit closer to each other. So instead of being a flat triangle like we have up here, we're now going to have a triangle in a pyramid down here. One more guy to look at. I'm going to get rid of some of my scribbles so that we can actually see the data table. All right, so what if I have 2 lone pairs and 2 bonding groups? So this guy, we can see the bonding groups are here and here, but there are also 2 lone pairs of electrons, and these guys are taking up space. I have a total of 1, 2, 3, 4 things on that central atom, so I'm going to call it tetrahedral when I'm looking at my electron domain geometry. But if I'm thinking about just the molecule and I want to get rid of those electrons that are taking up space, or I don't want to consider them when I'm thinking about this shape, then the shape is going to be once again bent. Kind of like this guy up here was bent, this guy is also bent. But the bond angle is going to be a little bit different. Here it was less than 120. Here, because I basically have 1, 2, 3, 4 things, I've got that non-bonding pair here, that non-bonding pair here. 4 things makes 109.5. This bond angle is going to be a little bit less than 109.5. 1 non-bonding pair of electron makes it a little bit less, like 107. But I've got 2 non-bonding pairs of electrons here, so these guys take up more space. And so we actually go down to about 105 degrees. So we're going to have less than 109.5, just about 105 degrees. Good. So that's a lot of information on this page. We're going to go ahead and do some practice problems and make all of these guys make more sense. First example, CO2. So what we need to do is start by drawing a Lewis dot structure, and then we're going to use that structure and VSEPR theory to predict the shape of the molecule. Lewis dot structure for CO2, carbon's going in the middle, oxygen is going around. We are going to put electrons between our atoms first. Carbon has 4, oxygen each has 6. 6 times 2 is 12, 12 plus 4 is 16 valence electrons. I'm going to go 2, 4, 6, 8, 10, 12, 14, 16. I have run out of electrons, which means I need to make some double bonds. I'm going to take away from here, and I'm going to make a double bond here and a double bond here. I have 2, 4, 6, 8, 10, 12, 14, 16 electrons in my Lewis dot structure, and each atom has 8 electrons. So now I'm going to focus on my central atom and thinking about VSEPR and that central atom. Central atom is going to be carbon. Carbon right now has 1, 2 bonding groups and 0 lone pairs, which means that if this is my carbon atom, and this is my oxygen atom, and this is my other oxygen atom, I would call this a ball and stick model. The shape is going to be linear. I can make a linear molecule with carbon dioxide because there are no non-bonding pairs of electrons here. 1, 2 bonding groups, 1, 2 bonding groups. That's going to make this molecule linear with a bond angle of 180 degrees. 180 degrees from here to here. Good, good. Let's look at this guy, H2CO. Carbon has 4 electrons, oxygen has 6, hydrogen each has 1. 1 times 2 is 2. 2 plus 4 plus 6 is 12 electrons total. Carbon's going to be my central atom. Oxygen's going to be here, and then I'm going to have hydrogen and hydrogen. I'm going to start with 2, 4, 6, 8, 10, 12. We are so close to being 8 is great, except for hydrogen, which is happy with 2. Except carbon right now only has 6 valence electrons instead of 8. So I'm going to steal away from oxygen. We're going to make a double bond right there. So now I'm going to use VSEPR theory to predict the shape of the molecule. We need to think about the lone pairs of electrons, and we need to think about the bonding groups of electrons that are on the central atom only. We only care about that central atom. And this molecule, carbon, is my central atom. There's 1, 2, 3 bonding groups around the carbon. Carbon has 1, 2, 3 bonds around it. Now granted, one of those bonds is a double bond, but it's still 1, 2, 3 total bonds around my carbon. So here's my ball and stick model, and I can see from this that I have bond angles of 120 degrees, and I'm going to call this trigonal because it clearly makes a triangle, but it's a flat triangle. So I'm going to call it trigonal planar. Trigonal planar. Good. All right, let's do another one. O3, this is ozone. So oxygen gas is O2, ozone is O3. Each one of those oxygen atoms has 6 electrons. 6 times 3 is 18 total electrons that I get to work with. So I've got oxygen, oxygen, oxygen. I'm going to start between. I have 2, 4, 6, 8, 10, 12, 14, 16, 18. We're so close. I just need one more pair of electrons on the central oxygen. How I'm going to do that is actually steal from here so that I can make a double bond here. And now each of the oxygens has 8. So there's 8, and there's 8, and there's 8. So looking at my central oxygen, that central oxygen has 1 lone pair of electrons, and then it has 1 bonding group, 2 bonding groups. This is a double bond, but it's still 1 bond. It's just a double bond. So I've got central atom oxygen, bond, bond, and this lone pair of electrons. I have altogether 1, 2, 3 things on that central atom. And so my electron domain shape considering all those things, is going to be called trigonal planar again. But the molecule shape is going to take into account only where I have the atoms. So I'm not going to worry about these guys here. I'm only going to worry about where we have the atoms. But these guys are still taking up space. And so our molecule is going to be bent, and it's going to have bond angles of less than 120 degrees. So remember, when I'm thinking about those three things, there's 120 all the way around, but this guy, 120, is going to be a little bit less because these guys take up a little bit more space. Less than 120, maybe about 118 degrees for that bond angle. All right, let's do a couple more. Carbon tetrahydride, carbon hydride, tetrahydride, CH4. Carbon has 4 valence electrons. Hydrogen each has 1. 1 times 4 is 4. 4 plus 4 is 8 electrons. Carbon's going in the middle. We've got hydrogen, 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 hydrogen all around that carbon. I'm going to put my pairs of electrons between. So there's 2, 4, 6, 8. Now I can use VSEPR theory to figure out the shape of this molecule. My central atom is carbon. There's 1, 2, 3, 4 bonding groups around it. Our prefix for 4 is tetra. The shape of this molecule is tetrahedral. So I'm going to have this guy, and then we're going to have 1, 2, 3, 4 things around it. Now some of these are going to come out of the screen toward us, and some are going to go back into the screen away from us because we're thinking three-dimensionally. Our bond angles are going to be 109.5, and this is going to be called tetrahedral. All right, let's do this guy, pH3, phosphorus trihydride. So once again, phosphorus, 5 valence electrons. Hydrogen each has 1. 1 times 3 is 3. 5 plus 3 is 8 electrons. Phosphorus is going to be in the center because hydrogen is never, ever, ever in the center. We're going to put those valence electrons between our atoms first. There's 2, there's 4, there's 6. I have 2 more electrons, 1 more pair to get to 8, and we're going to put those just on the phosphorus. So now thinking about VSEPR theory, my central atom is phosphorus. Phosphorus right now has 1, 2, 3 bonding groups and 1 lone pair of electrons. My electron domain geometry is going to count all 1, 2, 3, 4 things. That's going to be tetrahedral. My molecular shape is going to take into account only where I have atoms at the ends of those electrons. And so I'm really only thinking about where, oops, I erased the phosphorus, where I have hydrogens. So I've got phosphorus, I've got hydrogen, I've got hydrogen, I've got hydrogen. That non-bonding or lone pair of electrons are still up here taking space, but I'm only thinking about where I have my atoms. This shape is going to be called trigonal because I have a triangle here. I have a triangle with those hydrogens. I'm going to call it trigonal pyramidal, not planar, but pyramidal, because that lone pair of electrons are pushing those hydrogens down and away because these guys take up more space. Trigonal pyramidal. Bond angle of less than 109.5. Because these guys are taking up a little bit more space, they're going to squish those hydrogens a little bit closer to each other, maybe like 107. All right, one more, my friends, and then we are calling this lecture done. H2O, water. We're going to put oxygen in the middle. Hydrogen is going to go around the oxygen. Hydrogen each has 1 valence electron times 2 hydrogens. Oxygen has 6. 2 plus 6 is once again 8 electrons. We're going to put them in pairs between. There's 2, there's 4. Hydrogen can each only have 2, so those hydrogens are already full. So those last 2 pairs are going to go to oxygen. Looking at my central atom oxygen. VSEPR theory, there are 1, 2 bonding groups, 1, 2 lone pairs of electrons. Because all together there are 4 things, 1, 2, 3, 4 things total on the oxygen, the electron domain geometry is going to be once again 4 tetrahedral. Tetrahedral. I'm going to have that oxygen, I'm going to have hydrogen, I'm going to have hydrogen, but I'm also going to have lone pair of electrons, lone pair of electrons. Because we have four things, bond angles are going to be 109.5. We're starting at 109.5. But these guys take up a lot of space. They take up more space than do the bonding angles. So these guys are actually going to get squished together a little bit more. Not just a 107 squished together, but 2 lone pairs are going to squish it all the way to like 105 degrees. So this bond angle between the hydrogens is going to be just about 105. We did it. We defined VSEPR theory, valence shell electron pair repulsion. We distinguish between those lone pairs of electrons and the bonding groups of electrons on the central atom. We always only care about that central atom. And then we used those lone pairs and bonding groups to predict molecular shapes and electron domain shapes based on VSEPR theory.